Hello, everyone. Thank you for joining us. As people join in, we will start in just a couple of moments, not minutes, but a couple of moments. Through today, as you have any questions, please put them into the chat function, and we will respond to those questions at the end of the presentation. Again, as everybody joins in, thank you very much for joining us today with this Bowman Center for Sustainable Energy sponsored webinar. And please enter any questions that you may have. You will be on mute. We will address the questions at the end of the session. This webinar is being recorded and will be posted on the website for the Bowman Center soon. All right. Looks like we've got pretty much everybody who's ready. So hello, everybody. My name is Marshall Kern. It's my privilege to be the president of the Bowman Center for Sustainable Energy, which is a federally incorporated nonprofit sustainable energy think tank. The associates of the Bowman Center for Sustainable Energy have lived and worked across Canada, and our office is located in Sarnia, Ontario, on the traditional territories of the Three Fires Confederacy, with whom we acknowledge acknowledge their presence and their cooperation with us over the past while with a spirit of respect and friendship. Today's presentation is being recorded. This is part of an ongoing series of work projects that the Bowman Center has undertaken with Queen's University. And I'm very pleased now to introduce to you David Strong, who is the program manager whom we've been working with for a number of years. David.
Thanks very much, Marshall. Good morning, everyone. Again, my name is David Strong. I am a professor of mechanical and materials engineering, although most of the courses I teach at Queen's in engineering are faculty-wide courses. This program is one of those, which we refer to it as the APSE 480 multidisciplinary capstone design project. It is a final year capstone program where students from all disciplines can elect to take this course and have the opportunity to work in these multidisciplinary teams on real active external projects. And we're delighted to once again to have the sponsorship from BCSC to host this project. The students have been working on it since September through all of the various twists and turns, and I meet with them every week, and it's been a pleasure to watch the project move along. I'll just point out we've worked with BCSC for many years now through a multitude of different courses at Queen's, and again we want to express our appreciation for sponsoring these projects. This is, in this particular program, this is one of 8 projects that we have with different external sponsors this year. It's, as always, it's fun to watch all of them proceed through. So I'll pass it over to the student team to take it from here, and we look forward to your feedback and questions at the end.
Great. Thank you, David. My name is Damien Piquel. I'm one of the teammates along with Nathan Pacey and Frank Zhao. I'd like to first start by acknowledging that Queens is situated on a traditional Anishinaabe and Haudenosaunee territory, and we are grateful to live, learn, and play on these lands. So yeah, I appreciate everyone for coming out today and listening to our project presentation. And yeah, we can get started.
So, Damien, would you like to get started then? Can you?
Frank, you want to
Okay.
take over?
Yeah. Okay. Hello, everyone. So we have already introduced ourselves, and before starting with our discussion, can you go to the next slide, please? I want to first expand the concept of a virtual power plant. So what exactly is a virtual power plant? A virtual power plant is a network of distributed energy resources, also known as DERs, that is coordinated to function like a traditional power plant, but as a decentralized one. So it can generate and store and distribute electricity to consumers in the local area or supply it back to the grid. By aggregating distributed energy resources like solar panels, wind turbines, hydropower generators, batteries, and even demand-side resources like electric vehicles into a unified system, the virtual power plant operator is able to monitor and control these resources based on the factors like electricity demand or weather forecasts. Oh, sorry. It can not only help optimize the utilization of these resources based on factors like electricity demand, weather forecast, but also provide various grid support services like frequency regulation, load shifting. This refers to redistribute energy demand from peak time to off-peak time, and also enhance the resilience of the grid by providing backup power during emergencies and outages. Next slide, please. Over the first half of the project timeline, the team was focusing on the design process, which includes two major phases: design ideation and design decision-making. So a number of brainstorming sessions were held to generate initial ideas for the virtual power plant system designs. And we have identified that there are going to be three main subsystems, includes energy generation subsystem, energy storage system, and electricity management system. After that, a Scamper was then used to innovating the energy design ideas by modifying, merging, and adapting existing ones. So after that, pros and cons tables were then used to evaluate ideas and narrowing them down. So when it comes to the second phase, the team first talked to the clients and contacted with multiple stakeholders to ask for their needs and wants. And after that, a quality function deployment, also known as a QFD matrix, was then developed to identify the importance of each engineering factors based on stakeholders' needs and the project scope. It turned out that power generation and storage were the most crucial ones. And finally, weighted evaluation matrix was then developed for each subsystem to determine the ideal solution at the time.
All right, so after we did our decision making and ideation, we took a look into some of the technologies that we found and talked to suppliers in industry. So first we started with solar panels. In our initial investigation, we were looking into PERC panels, monocrystalline, polycrystalline, and thin film, just to like get an idea of the ballpark efficiencies and like cost to watt ratios. And after we had some discussions, we ended up talking with CanSolar about their 575-watt solar panels. They use the new TOPCon technology, which is a new technology introduced in 2013 in comparison to the PERC, which were introduced in 89. And so these new panels use monocrystalline bifacial half-cell modules. And they have a better efficiency than the PERC panels with 22.2%, and they have a lower degradation rate. And then these panels have a surface area of like 2.5 meters squared, an operating range of -40 to 85 degrees Celsius, and they're rated for a snow loading of 5.4 kPa. All right, so for the photovoltaic installation, we talked to OPSUN. They do a lot of projects across North America, and they have their mounting systems are rated for a snow load of 4.8 kPa and winds up to 290 kilometers an hour. Nathan, could you hit the next slide? So for the rooftop design, as shown in the box there, there are performance and budget options available. The performance more so designed for bifacial modules that can also utilize light coming in from the backside of the panel. And then there's also the budget option, which is more so for darker rooftops, which will use the monofacial panels. And then next slide, Nathan. And then we have the carport installations, which are, they come in the Y, A, and T shape orientations, as shown in this image. And they're all water managed, so you can designate where you want the water to be exited or managed to. And the frames are galvanized steel H-beam frames, and they use aluminum rails to mount the panels. And then, yeah, they've done projects all across Ontario and North America, including this one in Quebec. They do projects ranging from 20 kilowatts all the way up to 5 megawatts. And the next thing we looked at were wind turbines. We ended up getting in contact with Aeolus. They're a wind turbine manufacturer based in the UK, and they have small-scale wind turbines all across North America, Europe, and Asia. So this turbine here is the 100 kilowatt wind turbine. It has a start speed of 2.5 meters per second, a max power output for wind speeds of 11 meters per second, and a survival wind speed of 59.5 meters per second. And this turbine has an operating life of about 20 years, and tower heights come in 24, 30, and 36 meters. And we use this power curve here for the majority of our calculations, as Nathan's going to outline later in the toolkit. And lastly, the batteries that we were looking at, we were initially looking at some 500 kilowatt hour batteries from different suppliers, but we ended up going with the Tesla Megapack option. It came with installation already included in the price, which was a big factor, and they're a very reliable supplier for these batteries, as they do a lot of electric vehicle and battery research. And so for the Tesla Megapack, it comes in either a 2-hour or 4-hour option with their respective power and energy ratings, and they have their round trip efficiency of 92 or 93.7%. And they have approximate dimensions of 7.1 meters by 1.6 and a height of 2.5. And for their operating temperature, they can work in -30 to 50 degrees Celsius. All right, so now we can do the financial analysis, which is just a cost breakdown of the components to start. So after talking with CanSolar, they estimated for a 4 megawatt scale project, the cost of panels would be about 40 to 45 cents per watt. And these panels come with a 30-year backed performance and manufacturer warranty by a backer back in Germany, because of their Bauer panels are supplied from there. And then OPSUN for their rooftop installation, for the performance version, it comes as 32 to 41 cents per watt, and the budget is 20 to 29 cents per watt. And both of these come with a 20-year warranty as well. And then the carport installation was approximately $1.30 to $1.57 per watt, also with the 20-year warranty. And next, Aeolus gave us a quote for around $170,000 for their turbine, and it comes with a 5-year warranty. However, it does exclude installation and shipping costs. So we additionally did some research and found an Ontario study that estimates the cost of wind generation to be approximately $8,000 to $11,000 per kilowatt. And then for the Tesla Megapack, the 2-hour option was approximately $1,500 per kilowatt after the USD to CAD conversion. And once again, this came with installation, so that was one of the big factors for us deciding on it. And then we found a 480 volt transformer from Larson Electronics, and that was approximately $390,000. And so now onto some of the financial approximations that we did. We did a solar sensitivity analysis, which we used to find the total generation for different system sizes. This used a combination of both rooftop and parking lot systems, so the rooftop generation or carport installation. And so what we did, we found the total generation for each system size and then subtracted the Western Research Park's consumption patterns. And then we were able to sell the excess electricity and also add the amount saved from the consumption. So we use that to generate the revenue. And next slide. And then using this revenue and some degradation for the panels, we were able to find the payback and ROI over the projects for a selling price of about 10 to 40 cents, just to find the highs and low ends of the scale, like kind of the best and worst cases for any project. And so we found out that for the larger system size, obviously there's going to be a much larger upfront cost, especially when you go to the carport solution, because that's where the installation gets really expensive. And yeah, so the payback period obviously drops off as you get into higher selling prices. And then same with the ROI. The larger system sizes, they had a lower ROI for the lower selling prices, but once you get to around 18 cents, the larger projects actually get a larger ROI over time. And then we basically just did the same thing for the wind sensitivity analysis. We varied the amount of units that you could use on a site, and we ended up using the lower cost approximation for the study that we found, the $8,000 per kilowatt, just to find the approximate payback period for these turbines. But this is also very dependent on the wind in the area, as obviously the more wind you have, the more power you'll be able to create and sell back to the grid.
So while Damien and Frank went over some of the specific design solutions that had been proposed for the Western Sarnia-Lambton Research Park, we also wanted to come up with a solution that could work not just in Sarnia or not just even in Ontario, but actually all across North America. So to do this, we wanted to generate some software simulations that could actually take in your postal code and some site planning information and actually generate outputs based on a virtual power plant anywhere in North America. So how did we do this? Where did we start? Well, we first started with the data considerations and what modeling we needed to take in to actually figure out what solar and wind generation looks like, as well as battery storage across North America. So in order to do that, we needed to access data in an understandable way, taking into account considerations like the average irradiance for a day on an hourly basis, additional parameters like the elevation, the temperatures and pressures of your specific site location, and anything that would affect solar or wind generation. There was particularly difficulties to find data sets that had enough hourly data on these parameters in order to actually come up with good generation estimates. So for solar generation, we started with the NREL, the National Renewable Energy Laboratories database, known as PV-WATTS. And we accessed it using Python, a programming language, where we could put in some simple inputs like the system's capacity or the amount of solar cells and their total rated wattage when you sum them all up. Then you could put in items like the type of module you have, whether you're using a premium solar panel, a standard one, a thin film panel, and the respective efficiencies that are associated with it. As well, this API allows us to input different mounting types. There's going to be a significant difference if you have solar mounted on a roof versus a carport, and whether you have axis tracking or not, whether it's following the sun or not. It's going to give you different solar irradiance on the array and subsequent generation differences. So this database in NREL is actually used not only in North America, but all across the world for planning of these types of projects. They're used by the Department of Energy in the US for planning their federal projects, but they're also in cahoots or working with corporations like Google and ExxonMobil and different energy companies all across the world. So as well, some of the type of parameters are the orientation of the panels themselves, including the tilt and azimuth angle. And then you can even specify additional settings like the amount of loss across your system, the inverter efficiencies, and some of the ratios associated with orientations. So when we put in our inputs for a specific location, what do we get as outputs? Well, first off, we get the actual amount of irradiance on an hourly basis that we can use to calculate our generation. So you can see here the average plot of January to December, so a year-long monthly average of the solar irradiance, as well as its associated DC monthly generation from solar. Now, also some of the outputs are things like the temperature on the cells, so the cell temperature, and also the ambient temperature, which are actually used to calculate the generation values. As well, we get the information of where this data was taken from, which helps us understand how close it is to the site. If you had a site that was about 10 kilometers away, it might have a drastically different ability to predict what your site is versus if it was only a few meters away. So how did we validate this information? Well, we did a number of things. We looked at sites that we proposed all across North America. So we took postal codes and areas all across Canada and the US and parts of Mexico even, and we looked at how their temperatures and subsequent solar irradiance looked. So this is an example where we used Sarnia, where we took the average plane of array irradiance, solar irradiance on a monthly scale as predicted by the toolkit, and we compared it with the historical averages for shortwave irradiance in Sarnia. And as you can see, the months of June and July are where the maximum irradiance occurs at about that 7 kilowatt hours range. And in both the simulation and in the historical averages, they come up to exactly the same, showing that the Canadian winter months have much less solar irradiance, and we expect those peaks in the summer months. As well, we can see that the cell temperatures are actually a couple degrees, 2 to 3 degrees higher than the actual ambient temperature. And when we compare those temperature ranges from the toolkit to the historical averages, they also align quite closely. As well, when we compare the actual generation to historical generation sites, there was a great degree of accuracy. So this was just a methodology of validating some of the solar generation. So similarly, we had to find wind data, and we had to access it in a similar way. Now that we have solar generation data for all of North America, we want to be able to also generate wind power outputs for the same set. We want to be able to just input one location and understand how that impacts both types of energy generation. Now, wind generation can be a bit finicky. We know that when you're on the ground, the wind speed can be drastically different than if you're 10 or even 100 meters up from it. And this has large impacts on wind generation. So we needed to find a database that not only could interact with the solar location sites well, but could also have a gradient of different wind speeds that it outputs so that we can understand at each height that we have our wind turbine, what that wind speed and subsequent wind generation looks like. So to do this, we used a database called OpenMeteor, and it accesses different databases from actually all over the world and not just North America. But this fit well because we could feed in our location from our station input from the solar generation, and we could get wind speeds from 10 meters to 100 meters. To validate it, we actually looked at another database called StormGlass.io, which also takes its data from North American oceanic reviews, and it's used across different companies in the US for wind turbine generation specifically. And when we compared the daily and monthly wind speeds from both these databases, they came out to quite close for different sites across North America. So when we actually look at the wind speed output, we use Sarnia again as a test case here, where we can look at the historical average wind speeds and see that on average, the months, summer months have less windy than some of the winter months. And we can also see that from our 10 meters to our 100 meter point, they fall perfectly within the lower and upper bounds of the historical average wind speeds in Sarnia. So this shows that this database or this API tool can actually help us generate wind speeds that we can use to find subsequent wind power generation. So this is exactly what we did. We took the data from our 10 to 100 meters, and we did some interpolation methods. So you can see on the right here some of the interpolation methods for a few hours of a specific date that we produce with the toolkit. And we go on an hourly basis, taking that curve from the Aeolus wind turbines data sheet, and we actually fit at multiplying it by this curve to understand the associated wind generation power output for each wind speed. So for each hour at each height, we have a specific generation for your specific site. So we then take those hourly generations and sum them up into our daily wind output. Of course, this is on a per wind turbine basis. So, you multiply as you have more wind turbines and at different heights. And then you can subsequently find your monthly and yearly generations and their subsequent revenues. So this led us to our final system, which is the battery storage and simulation. So battery storage or energy storage in general for virtual power plants offers a specific benefit. We know that different types of buyback pricing for energy can have hourly ranges. There's peak demand hours that have a specific opportunity when you generate energy through solar and wind, which aren't necessarily on demand. It means that solar and wind are not going to generate in the same time period when hourly prices are at their maximum. So this outlines the potential to store some energy and actually sell it back to the grid at a higher price than you could if you sold it right away. So in order to come up with a size of our battery, we need to understand how this pricing model works. And specifically, we took a look at the Ontario hourly energy prices as published by the IESO for the past 3 years. So in order to understand what size battery we wanted and how we wanted to charge it, we needed to understand what sort of algorithm we could use to identify arbitrage opportunities and make sure that we're maximizing profit from our clean energy generation. So like I said, we looked at the past 3 years, and you can see this in the plot here. This is the average HEOP or hourly Ontario energy pricing across 2021 to 2023. Now, this is looking at a daily basis, which is what we found made sense to look at because there's different times of the day where everyone's using a different amount of electricity, and it goes down at night when everyone's asleep or not working as much. And this was also true to be said that from the hours of 5 p.m. to 8 p.m. was some of the peak demand pricing. There, of course, is a variance on a day-to-day basis, and that's exactly what we wanted to look at. So we use different algorithm types, a lot of which come from financial modeling. We started with a 24-hour moving average, of which if the price was higher than the previous 24 hours, we would theoretically charge the battery. And if it was lower, we would discharge the battery. For a 4 megawatt hour battery that's simulated with a discharge rate of its entire capacity within the hour, we found that the 24-hour moving average generated a revenue of approximately $22,000 a year. As well, we looked at the actual hourly next predicted price, or the next 3-hour predicted price, as published by the IESO in their hourly data. We found that this wasn't actually as good as being profitable as the previous 24-hour moving average. As well, we utilized a stop-loss strategy, so that's something that you see traders doing often in financial analysis, but that also didn't particularly work as well. The last thing that we actually evaluated was using a machine learning model called a long short-term memory unit. Now, these units are actually optimized for temporal analysis, so they're used for time series data. And we found this, along with the 24-hour moving average, to work quite well in comparison to the other algorithms. But what all of these algorithms showcased and where they worked well is when they charged at the lowest demand pricing on a daily basis and just discharged at the peak hourly pricing. This meant that for our toolkit generation, we wanted to come up with battery sizes that would be charged and discharged on a daily basis from the low hourly pricing to the peak pricing. So as well as our charging and discharging model, we had to come up with something that simulated the actual degradation of batteries. Now, batteries have a very specific type of degradation that's associated with the amount of cycles they go through, the amount of charging and discharging during their lifetime. Now, in order to actually understand how batteries degrade over time, you actually want to look at how much you're filling them in terms of charging and discharging. So there's minimums and maximums that different cycles use a battery called their state of charge. In the plot here, you can see that we're evaluating different states of charge, whether they go from 25% charged to 100% charged, or whether they only go from, let's say, 75% fully charged to 65% charged in their charging and discharging realms. So when you do that and you look at about a year's worth of cycles, if you cycle once per day, you can see the first stage of discharging, which is kind of that out of the box, or you can see that cycle number A. Now, this discharging model was actually incorporated from a 2016 study on lithium ion grid scale batteries at 20 degrees Celsius. Now, it should be noted that batteries have improved since 2016, so this is a bit of a conservative estimate, but it gives us a good idea of what stages of a battery life look like and how we can actually incorporate energy storage into the toolkit simulation. So, like I said, we looked at this 2016 study and we found that there was 4 distinct states of charge. So we've identified them here in our model where we have the actual degradation of the battery over its cycles for each stage, ending with a simple degradation in D over all of the state of charges. And you can see their subsequent capacity retention, which means that the minimum they have in comparison to their out-of-the-box capacity rating. So those were all the systems we incorporated. Why don't we actually take a look at the toolkit itself? So here I'm at our homepage of the toolkit, and you can see that I'm looking at the different, you can see that I have the different inputs for display as long with the equipment details themselves. Now I'm just demonstrating here the dynamicness of having a web application. In the toolkit, you can also access all of the different data sheets for the equipment that we sourced. So you can see that we have the different solar panels, whether they're premium, standard, or thin film, along with their data sheets, as well as all the subsequent equipment like the wind turbines, the batteries, the transformers, and all their subsequent mounting equipment, all able to be seen in the homepage of the toolkit with their subsequent specifications and data sheets. So here you have some of the inputs at the top of the page. So it starts with your location. Where is your site actually going to go? So you put in a postal code that works for any site in North America, or any that we've tried, I should say. And then we have the solar inputs, where you start with the amount of surface area you have available. You can choose the different array types. So whether that's going to be a carport or on a rooftop mount or 1-axis tracking or 2-axis tracking. Then you can select whether you want premium, standard, or thin film solar panels, along with the actual tilt that they have on your specific site. Then moving on to wind inputs, you can put in the number of turbines you have and the actual height that you want them from 18 to 30, I think it's 36 meters tall. Lastly, you can choose whether you want to store battery, whether you want energy storage, and you specify how much you actually want to store and the final specifications of what degradation you want. So how many cycles can your battery last and what percentage should it go to? So when we input this, it takes us to the solar page where we have some of the input parameters that got put in from the toolkit. And then we have some of the outputs like the total system capacity, the yearly total generation of DC and AC, along with the number of panels that's associated to that. And then we also have some of the things like the upfront cost of these systems that are dynamically generated, along with some of the project metrics like payback period on a specific buyback pricing and the associated return on investment with that. Then as you scroll down, you can actually see the monthly generation. And we have some dynamic plots there where you can actually zoom in and look at each data point on a per monthly basis or for each actual data point itself. So you can see there I have the cell temperature along with the ambient temperature, and you can scroll over them to just exactly see what the actual data is itself. As we go to the bottom of the page, just like Damien mentioned, we have some sensitivity analysis. So we can see what your system would look like if it generated a bit more or a bit less power output per year. And we range the buyback pricing so you can see what your actual project metrics would look like in terms of payback period, return on investment at different amounts of generation per year and different buyback pricing to help you identify how feasible your project will be. So you can see here that the calculated yearly generation is the line in red. And you can actually zoom in and scroll over to see your payback period in years associated to that generation. And like I said, it's dynamic, so you can zoom in, zoom out toggle. You can even save your image if that's something that you want to do. As well, we have the return on investment. And here I'm demonstrating, you can see where your investment becomes profitable at a specific buyback price for each yearly generation. And we also have the revenue in years along with the degradation. So that's taking the average degradation and turning it into a yearly revenue. At the bottom here, I'm actually showing what the hourly pricing looks like. If you were to sell solar back at the Ontario hourly pricing, what that would look like, along with its total yearly solar revenue associated with that. And you can zoom in and see actually like peak generation days and what their buyback pricing is going to look like in terms of revenue. So that's some of the system outputs for the solar generation page. Before I move on to wind, I'm showing the location input. So we actually looked at Google Maps API, where you can see exactly where your data is being sourced from. So you can see exactly how far from your site, at least from how far from the postal code inputted, your data is coming from. And you can also see on Google Maps exactly where that is if you're curious, along with some things like the elevation and the latitude and longitude, along with the inputted postal code, to make sure that your data is exactly where you want it to be from. You can see here, I'm just looking at a site in British Columbia. So now moving on to the wind generation page, you can see that it has a lot of the same inputs and outputs as the solar page in terms of those project metrics and the upfront cost of wind, depending on your inputs that are dynamically generated. Oops. We also have the monthly average wind speeds along with their specific logarithmic fitting. As well, we have this interpolated data with the actual wind speeds on an hourly basis that enables you to zoom in and see how that looks like for each month of the year and each day, along with the hourly interpolated ones. You can also see how your wind speeds change on a day-to-day basis. What hours of the day can you expect to be the windiest and which are not, along with the actual generations on a monthly basis, and then those same sensitivity analysis that we looked at for solar, we also look at for wind generation. And then, of course, we also look at the hourly buyback pricing at the very end. So that leaves us to the battery simulation page, where we can see our specific inputs and outputs again with the project metrics, along with our degradation for a year long of each state of charge, and then the actual state of charge over the lifetime of your specific battery inputs. Then we actually show you what your revenue would look like when you sell back at the arbitrage price, so that hourly energy price for each state of charge of the battery system. So with each one of these systems, you can see your project summary and how feasible your project is going to be. Since we have wind here in British Columbia, it wasn't a very profitable project since it's not quite windy in British Columbia in the mountains there. Sorry, I'm having technical difficulties here. Sorry about that. So what did we actually learn from the application design? Well, like I said, we can compare different sites. So for an example, we compared Austin, Texas to Sudbury, Ontario for solar generation. And as expected, Austin, Texas is much sunnier, much warmer climate than Sudbury would be. So you can see that for the actual power outputs on a yearly basis, for the same system with 200 meters squared surface area and a 28-degree tilt using premium panels, Austin was consistently generating more electricity, or more power output, I should say, using their solar system, with a payback period of just 19 years as compared to Sudbury's payback period of 23. And associated with that, Austin's project for this solar farm would have a return on investment over a 30-year period of 58% as compared to Sudbury's 32% return on investment. So that shows you that you can compare different sites for solar farm analysis. As well, you can also look at just wind generation. So we took a particularly windy spot, Gander, Newfoundland, and compared it to a not so windy Kelowna, British Columbia. And you can see the major difference in wind speeds and the subsequent return on investment that creates. So for a single 30-meter turbine, you have a return on investment of 228% for Gander, as compared to Kelowna's return on investment of negative 97% over that 30-year period, with the associated payback period in Gander of just 9 years, as opposed to Kelowna's almost 380 years payback. So what are the key takeaways from some of the toolkit simulations? So we can see that solar is much less location dependent than wind, in terms of the fact that we have not just the light that we see that's involved, but ultraviolet and infrared lighting that actually generates solar generation throughout the day. Compared to wind, where we saw with Kelowna and Gander, there was a huge difference in its ability to generate power. So the wind speed directly affects the generation much more than the climate impacts solar panels. As well, what we saw across almost all the projects that we compared, or all the sites that we compared using the toolkit, was that battery storage has a limited profitability over the lifetime of the projects. So we saw that the hourly buyback pricing, as published by the IESO, wasn't actually beneficial for projects to have battery storage, which means that when we implemented our toolkit, you have to specify the amount of storage you want, and you have to select battery storage as a particular input. This is because the sites that it makes sense for are things like hospitals or different manufacturing plants, where they have a specific interest in reducing their ability to have outages, or they have a specific profit generation capacity of keeping their electricity going throughout the day. So it turns out as well that for a positive return on investment, the buyback pricing had to be on average larger than the hourly Ontario pricing as published by the IESO. So that just shows that there's a specific need for pricing and different grants in order to incentivize these clean energy projects. So for some future considerations of the toolkit, like I said, we use the Ontario average energy prices on an hourly basis, which means that when we look at places outside of Ontario, we're not necessarily getting the price that they would actually pay for energy, which means that, so if we wanted to improve upon that, we could actually gather the buyback pricing from the user input, or go find similar pricing analysis across different states and provinces in North America. As well, for things like the azimuth and tilt angle, the actual orientation of the solar panels, it would be beneficial to have some sort of optimized calculation for their orientation for the specific location. And what I mean by that is different sites might have a need, like if you're putting solar panels on a roof, to have a specific orientation, but there's going to be cases where you can situation a solar panel in any orientation, and it would be beneficial for site owners to understand what that optimal orientation is for their location. As well, for the wind simulations, we don't consider things like what type of environment you're in, whether you're in an apartment building with lots of different skyscrapers around you, or whether you're in a farmer's field. These are the type of things that will affect erosion and wind speed patterns that could better help us understand what wind generation is for a variety of sites. That's not just based on where the location of the data is coming from.
So other than the toolkit, a design was also proposed for the Western Sarnia-Lambton Research Park specifically. So the system design includes, next slide please, includes the OP sound wire-shaped canopies that can be installed at parking lots, the CanSolar TopCon panels over the rooftops and of the buildings and over the canopies, and Tesla Megapack 2 hours, which comes with the monitoring system, and Larson Electronics 480-volt transformers. And the Blue Water Power will be in charge of the grid interconnection. So what's showing here is a rough CAD model of the research park and the solar arrangement of the parking canopies and roof-mounted solar panels. So the implementation has been developed for the system design of the research park. Once we have our system design ready, it's necessary to obtain permits and approvals from local authorities and regulatory bodies, including the local municipal authorities, utility distributors, and Ontario Energy Board for construction and operations. The duration for this phase may vary, but it can typically take 1 to 3 months to finish. So next phase will be procurement. The designs require equipment and components like solar panels, batteries, mounting structures, inverters, and transformers will be acquired from suppliers. The CAN solar panels may take up to 9 weeks to arrive, while Tesla Megapack switch may require a 7-month lead time. Therefore, 7 to 9 months expected to take for this phase. And factory acceptance test ensures all the equipment meets specifications and undergoes testing at the factory before delivery. It may take a couple months to complete, but this phase overlaps with previous stages, so it won't add up to the leading time. And now it comes to the installation. OPSUN will oversee the installation of the carports and solar panels across the 3 major parking lots with rooftops and carport mounts. To maintain clear car paths for and allow for efficient snow removal, the canopies will be designed to cover only the parking space, preventing snows from falling directly on cars and potentially may cause damage. The parking lot consists of 8 rows, spans approximately 6,000 square meters, and support for a solar system capacity of around 900 kilowatt DC. If we add that value with a surface area of available rooftop areas, that give us approximately 12,000 square meters, and that's equivalent to around 4,600 solar panels, given that each panel may occupy 2.5 square meters. And Tesla certified professionals will handle the Tesla Megapack installation along with the associated transformers outside the parking lot on the top of the undeveloped land far away from the office. This is to ensure the ease of access for the maintenance and to reduce the risk. After that, the coordination with Blue Water Power Distribution in terms of the grid interconnection will be processed, and the whole phase may take around 3 to 6 months to finish. And after that, the mechanical completion verifies the installation that are correctly executed and fully operational. Specifically, the carport's durability against Sarnia weather condition will be assessed to prevent any risk or inconvenience to the research park employees. After that, the site acceptance test will assess the system's alignment with the project's needs using the project simulation toolkits that was mentioned by that was introduced by Nathan just now. And the pre-commissioning and commissioning phase checks the system's components and connections and tests the system's performance under actual operational conditions, other than instead of a simulation model. After that, we have to get approval from electrical safety authorities, ESA, for this electrical safety, and the system can start up once the authorization is issued when the system successfully passed the inspection. And a performance verification will be used to modify to monitor the output of the system to see if it matches the specific requirements and the client needs. It may last longer if the degradation of the system components will be monitored as well. So it may take from 1 to 6 months to finish. And last but not least, maintenance and monitoring phase is continuous and may last for the entire project lifetime. So regular maintenance including the cleaning of solar panels, checking the battery health status, inspecting the wiring and connections, the mounting and carport structures to ensure the proper functioning of the system. So periods of individual inspections may vary, depends on factors like climate and storage environment, but a comprehensive check will be performed at least twice a year. besides regular inspection, the virtual power plant should also be equipped with monitoring systems to provide real-time data on energy generation, battery usage, overall system performance, and subsystem degradations. So that, yeah. And a financial adjustment has been, a simulation has been conducted to evaluate the potential benefits of implementing such a virtual power plant for the research park, particularly in terms of offsetting their utility bills. As shown on the graph, that we can see that the first line is the actual consumption that we get from the that is used from the data was provided by ON. And the second line shows that's consumption data that was simulated out of the toolkit with 2 Tesla megapacks. And the third line shows that's consumption with 3 Tesla megapacks. So to summarize the table, at bottom of the slides, around 79 kilo around $79,000 could have been saved with 2 Tesla megapacks with a total cost of around 12.6 million Canadian dollars, and around $106,000 could have been saved with 3 Tesla megapacks with a cost of around 15.5 million. Yeah.
All right, so now a little bit about the safety considerations for the system. I think it's important for the physical implementation with the carport solutions in the northern, like in Canada or like northern USA. There's going to be snow and ice buildup on the mounts, which is important to be managed properly and to get rid of so it doesn't injure anyone, fall on anyone. So this can be easily done by either using a soft brush on the panels, or you can use some warm water just to melt it all away. And obviously the water management system will dispose of that. And then also having on-site lithium batteries is quite dangerous if there's any fires that take place. However, it's with the Tesla Megapacks, they do a lot of fire safety testing, and they also, all the batteries are like individually contained, so that should ideally keep them keep any employees that are working nearby safe, ideally. And then also, as Nathan was saying, with the state of charge, you can definitely adjust that to ensure that you don't drain out the total capacity of the batteries too quickly. And also, they will be placed a bit further away near the carports and away from any buildings. So, and then also with the software usage, probably the most important consideration for safety is just data leakage. So ensuring that there's strong encryption protocols whenever transferring sensitive data is very important to consider. And then on to legislation. So connection to grid, we had discussions with Blue Water Power and Alex Palamaca, and we found that for a generator that's typically less than 10 megawatts, it would connect through an LDC, while more than that would connect directly to Hydro One. So after you figure out the system size, you can fill out a DER application form, and that would be submitted either to the LDC or Hydro One, containing project specifications like the system size, interconnection diagrams and drawings, and site information, stuff like that. And then after you do that, then you'd also have to do a connection impact assessment, which would be submitted with site specifications, contacts, and then project information and interconnection components again. And then also there would be structural permitting for installing carports. There'd be an accessory building. So you'd need to submit a permit with any city that you'd be building this in, either whether that's Sarnia or any building across Ontario or Canada or the States. And then there would also be the solar system permits, which would require like fastening information, system info, which would once again also have to be submitted with the city. And so I think a very important part of this project is the feasibility of these systems themselves. So at the moment, with the current regulations in place, these systems aren't actually possible to implement. Ontario only has a net metering program, which allows you to sell generated electricity back to the grid, and you only receive credits for that sale rather than actually making a profit on it. So the IESO is currently trying to implement a market renewal program, which will help make the grid more operationally and financially certain. As there's been a lot, and then further, there's also been inconsistency in like government programs, like the microfit and fit programs being canceled a little while ago, which deters investment from international investors, which doesn't help our grid infrastructure and economy grow. So we think that implementing virtual net metering would allow these virtual power plants to become more feasible. You'd be able to sell electricity either back to the grid or to the surrounding community, and you'd actually be able to generate revenue when you sell this excess electricity. And so these regulations are currently being tested in London, Ontario, and they've been proven already in countries like Finland, who have operating virtual power plants, and ones being currently built under like government contracts. So in conclusion, we have developed a dynamic toolkit to evaluate the feasibility of VPPs across North America using renewable energy generation and battery storage. And these are all the data is taken from real world data sourced from APIs, as Nathan was describing in the toolkit. And then this will produce all the financial metrics that are required to determine this feasibility. And then we also have created the Western Research Park implementation plan, and we have hopefully properly addressed regulatory roadblocks for the opportunities for Ontario to help boost grid infrastructure and help get these projects kind of underway in Ontario.
Well, thank you so much. And we want to take this moment to thank everyone at the Bowman Center. Specifically, we wanted to thank Ed and Peter, their generous support throughout the project. We also wanted to mention and thank our Queen's University teaching team, especially Professor David Strong, and some of our teaching staff like Jason Harris, who have been supporting us throughout this project. As Damien and Frank also mentioned, we've been consulting with various industry experts from companies like CanSolar and OPSUN, as well as industry experts on the grid side, representing London Hydro, Blue Water Power, and some of the installation companies we've worked with along the way. So we just wanted to thank everyone for coming out today, and also those who have helped us along the way. So we will be taking questions as well, but I'm also going to be putting up the toolkit for a live demo where we can take some suggestions and walk through as well. So yeah, I'm just going to get that set up now. Thank you, everyone.
Okay, thank you. David, did you wish to add anything from Queens?
Well, I guess I can say it now instead of at the end. Again, these projects are incredibly supportive of our young engineers' education. These are really great opportunities for the students to work on real projects. Now, these days, actually, Queens is up to about 50% of our students are now also doing full year, 12 or 16-month internships as well. So these experiential opportunities, be they external internships or working on these projects while they're actually still in their academic program, are just amazingly helpful to foster a very good start to their career when they leave, whether they're going on to work in industry or take further graduate studies. So again, BCSC has been a long-term supporter of our programs at Queen's. I think in this case, the students have done a great job with what they've produced. And I just want to thank the whole BCSC team for the input they provided, for the connections they've made, for the students. That's really helped with what the students needed to do. And again, our goal is to provide as much value to our external partner as possible. But the primary value, at least from our side, is the educational opportunity, and that's a home run. So thank you very much, and I'll pass it back to the students to take you through the toolkit. When we were talking about this yesterday, I said I think it'd be really fun to just demonstrate to everyone how this works, and so the guys will give you a chance to go through this.
Thank you. So Damien, please explore the toolkit with us.
Yeah, I'll let Nathan take care of that. He's the one sharing his screen, so yeah, he's got it.
Perfect. Yeah. So I'm just going to walk through what I think here shows it off the best. I know we had that little video demonstration, but so yeah, here you can see all the equipment details along with some of the data sheets we have and some installation manuals along with the associated websites. So like Damien mentioned, the solar panels we used are these Bauer Premium Protect ones as provided by CanSolar. So let's say you want to set up a solar farm. I'm just going to put in my postal code. I'm from Waterloo, Ontario. And why don't I set up a virtual power plant that utilizes a bunch of different things? So we can start with maybe a surface area of say 1,000 meters squared, and I have a house, so let's make it roof mounted with those nice premium panels. Now I know that actually from doing some simulation, the tilt is about perfect for Waterloo at about 34 degrees, so I can set it there. And why don't I put in some smaller wind turbines? We'll put 4 in my backyard. And then, well, I guess I'll need some battery storage there because I don't want my TV to go off during the Leafs game. I can't miss a goal. So why don't we put in 10 kilowatts? And geez, I think games run for 3 hours, so let's do that. And then I don't want my house to catch on fire, so I should probably make sure the batteries don't drop their capacity at the end of the lifespan. So I'll put it at about 50% or maybe 55%. And why don't I submit that? So then it gets the data pretty quickly, actually. You can see it's already run and put us on our solar page. Let's make sure that location was good once we are all loaded here. So yeah, that's where I live. Don't don't write that down maybe, but yeah, that looks good. So I can now take a look at my my solar inputs here. Can see that the summer months are higher. Makes sense. We have the cold winters, so I'm not generating too much in the December. We can take a look at the buyback pricing, some of the sensitivity analysis, and get those hourly pricings. Looks like there's a peak day here, so why don't I zoom in on that and see what insights I can get. Oh, if I want to go back, I can just double click. So you can see there's some pretty useful functionality, especially if you want to identify data. So we see on that peak day, profit of, I think, 40.45 Canadian dollars on that peak hour, with a total yearly revenue posted at the bottom there. Now, why don't I see what those 4 wind turbines were doing in my backyard? Hopefully not causing too much noise for my dog, but seems like it's not too windy, especially not at 18 meters. So I'm not going to be generating too much profit. Or sorry, it is generating profit. I read that wrong. With a payback period of about 17 years. I can actually zoom in and see for each month if I want to load up again, maybe see the start of the school year, how windy it is in September. So it reloads the page in order to go back and fetch September's data because it started on January for those wind speeds. And then once it loads there, I can zoom in on a specific day and see what the hourly wind speeds are looking like, which is what we use to do that generation. As well, I can see from my house what hours of the day are peak wind generation. Looks like it's pretty steady across each hour, but the months are not that case. So looks like December is going to be the windiest, followed by like March and February, and the power generation subsequently follows that. And then I have some of those same sensitivity analysis at the bottom there. So yeah, there were some questions I think as well on the toolkit, and we can we can address those maybe for a bit after, but we can see a similar case going on with the battery page and all the simulations for each state of charge. And then finally, we can go to our project summary page and see what this project would produce. And yeah, it's really easy to input your location, change some parameters, and get a pretty quick estimate of what you're looking like for project feasibilities.
Great, thank you. I'm very impressed with how quickly you're able to get the results in because you've looked at this more than we have. You're coming up with a very detailed analysis about profitability and payback, which is delightful to see. Anybody who's using this toolkit would probably have to spend a couple of hours to understand the outputs and be able to provide a detailed interpretation. And I recognize the research part that you just had on screen. As we proceed, I really want to add to my own acknowledgements and appreciation to the Sarnia-Lambton Western Research Park. I know that we have Dr. Ong U and Dr. Catherine Albion with us today. Our sincere appreciation for the contribution of expertise and time and for volunteering the research park as a site for testing. Also on the call, I noted is Alex Palamaca from Blue Water Power. And Alex, I'm very grateful for your involvement and encouragement, not just in this project, but over the past few years as well. And I'm grateful for the financial contributions that Blue Water Power came through with in support of this project and the Bowman Center for Sustainable Energy. But there are a few questions, and I'll start with one for myself. My background is not in energy, but in biology and environmental studies. So when I had the opportunity a few years ago to attend an open house at a solar farm, I asked the question, how come all of the solar panels are so close to the ground? Why are they not being placed 3, 4, 5 meters high so that other things could be happening underneath them? The explanation that I was given at that time was that as solar panels were put higher, they would be able to capture more of the prevalent wind. And so the design criteria had to keep the solar panels low so they wouldn't have to factor in any lift factors as the wind is coming predominantly from the north and lifting the solar panels off the support structure. Is that one of the design criteria that you encountered as well, or has that been designed out of the concerns by current manufacturing processes?
Yeah, I can absolutely take that. So I think the majority of the installation stuff that we found, like the mounting systems for carport and rooftop mounts from OPSUN, they have a wind rating of like 290 kilometers an hour. So it's much larger than anything that we've seen on in our research so far. So I think that it was taken into consideration, but it just due to, like, I guess the over engineering of that factor, we didn't really consider it like too heavily.
Okay, thank you. There is a question about battery degradation. And can the 2 or 4 hour battery rated system, is there any economic performance related to battery degradation? We know, and you mentioned it in your presentation, that there's been large strides made on performance in battery chemistry over the past while, but is there any comparable thing that you're aware of pertaining to the economic performance of battery degradation over the timeframes that you've looked at?
So yeah, that's a good point that battery chemistries have gotten a lot better in the past years. When we looked at battery degradation, we wanted to look at the same chemical makeup of the Tesla Megapack, which is that of lithium ion. So in terms of the actual financial ability for referring to battery degradation, we also made some assumptions that were on the more liberal side, whereas the degradation model themselves were on the conservative side. And the rationale was we really liked the study that we found on degradation, specifically those states of those different stages of degradation, because we thought that represented a good case for energy storage.
2060, that's 2060.
For grid storage themselves, it's not like the same as electric vehicles, let's say, where you have the substantial risk in electric vehicles for batteries to drop below a certain rated capacity in terms of having passengers on board. So we wanted to have a degradation model that could actually take the batteries to the capacity as low as 40, 50% or whatever you put in as your inputs. So this was actually kind of ties directly back to the ability for it to generate profit over time. I'm not sure I can speak too much in terms of the new battery degradation and how those models would influence it, because it is different for each type of chemistry, and it is different and changing rapidly year to year. Tesla comes out with new different types of chemical makeup, so as well as their casing on almost a yearly basis now. So it's definitely a moving industry that changes rapidly.
Sure, David will be noting that's an excellent response to a question that's kind of loaded, because even through the academic year that you've been studying, there have been changes and further announcements about battery degradation and alternate chemistries. So David, please take note of that. Good response to a probing question.
Oh, thank you.
Okay. And there's a question that gets into some of the understanding of the economics, which may be outside of your areas as engineers, but it looks like there's very high ROI values, but then again, a very long payback period. Can you comment on that?
Yeah, so I can also scroll to, let's say, the solar simulation, and I think what that
Nathan,
might
you're
be
not sharing your
referring.
screen anymore, just so you know.
Oh, thank you so much.
No worries.
Can you see it now?
Yeah, you're good.
Yes.
Perfect. Yeah, so I think what that might be referring to is the high payback periods on this y-axis. But this is actually referring to a specific buyback price as well. So that's at a low buyback price of only $0.02, so like 2 cents. Well, whereas you have some like lower payback periods associated with higher buyback pricing. So when we actually looked at our toolkit model, we were selling back, I think it was at 0.1. Yeah, 0.1, so 10 cents a kilowatt hour in Canadian. So when you actually zoom in, you can see the associated payback period for each one of those at 0.1. And that would be more indicative of the payback period that would represent that instead of those lower prices. I think that's what that's referring to, but please follow up with more questions if there was a specific figure that you wanted to note.
Okay, there's a question here in the room. Ed?
So were you able to, your economics are based on hourly average prices, but what were you, or could you use the model, I suppose, to do an analysis to find out what would the price of electricity have to be to make this, say, I think the microfit program at least had the approach is more or less a 6 or 7 year simple payout, a capital payout over 6 or 7 years. And so that's where we got these very high prices of electricity for that program. So what would the price of electricity need to be? 10 cents, 20 cents, 30 cents a kilowatt hour, so that this thing would pay out in 5 or 6, a utility grade investment. I guess I'm thinking in context of peaker plants. I think the levelized cost of electricity for that type of unit is really, really high. So what would the price of electricity have to be to make this thing look kind of, like I said, a secure utility grade investment?
Yeah, so I can speak to about the 20-year lifetime period. And what we found was in order to have a return on investment, you were looking at that 10-cent range per kilowatt hour. And that was why we wanted to use that as the lower bounds of our pricing model. If you were looking at more traditional investing, you'd probably want to go down in terms of your buyback price, or sorry, your payback period, which means like you'd subsequently go up in proportion to your buyback pricing. So say if 20 years is break even at 10 cents, you know, your 10-year payback period price would look more like 20 cents. But this is significantly different to the actual hourly pricing model from the IESO, where it has averages as small as 3 cents per year, I think, in 2023 around. So there is a significant difference between that pricing, which is something that I think is worth noting.
Thank you.
No problem.
So it's very clear to me that the design of this toolkit and the tool that you're sharing with us on screen right now had in mind preparing this for an investor who's looking for some profitability over a period of time. Is that basically the premise that you were working with?
Yeah, pretty much. Ideally, obviously, if you're trying to implement the system into any commercial site, any business is going to want to generate some form of revenue. I think with UNG and the Western Research Park, they were more so interested in the implementation of sustainable technology. So as long as the project breaks even, then that would be ideal. And then you have, like, you can say that you're powering your site with renewable energy. However, another site like maybe a mall or something, they'd be more driven on the revenue. So yeah, we wanted to figure out what sort of selling price you would need in order to gain a certain payback period or ROI that would meet the certain site's demands, ideally.
I can also see how this tool would be very useful for a local distribution company or somebody else who's wanting to resell the power in some capacity to be able to determine to be able to evaluate what the connections would have to be and what the costs they would incur would have to be as well. So you've talked about arbitrage, and you've also talked about the regulatory regime that would be needed to support this. Is there a way to look at this as well, how to evaluate the technical connections with a local distribution company and the costs that they might incur?
Yeah, I'm not too sure about the actual like connections from a grid side, like to a distributor from the like from a virtual power plant or from a distributed energy resource. That's something that I think is very dependent on the actual location and what you're looking at, whether you're in Ontario connected to Hydro One or whether you have your local distribution company. So it was something that we wanted to maybe take more out of the scope because we were looking at places all across North America, specifically for the toolkit. But it is something that for our specific site plan that we put in a bit more detail into.
Great, thank you. I appreciate the way that you've handled the questions, and I don't see any other questions that I want to bring forward to you right now. We've been going on for almost an hour and 20 minutes, so I'll say again, my sincere thank you to Damien, to Frank, to Nathan for the work that you've done. My thanks again to the couple of Bowman Center associates, Ed Brost and Peter Smith, who've been working with you on an ongoing basis. And our appreciation to Ong U of the Western Research Park and Alex Talamaka for their contributions out every now and then. I'll add that I know that very fine fellow from from our group was involved as well, that being Dean Jacobs, in providing some additional information to you as well. So it's been a truly a multidisciplinary, well-rounded exploration of this topic. And I thank you very much, David, for making sure that Queens was in touch with us so that we could bring this forward. And I'm grateful for the report. I'm looking forward to the hard copy research to be delivered to us. With that, unless somebody else has a pressing question to post in the chat, or Damien, Nathan, Frank, you have a final comment, we will bring this session to an end.
Thank you so much.
The only thing, sorry, Nathan, if I could, just to clarify, as always, we're in the what I call the report cycle with the team right now. And what I'll do as soon as everything is complete, signed off, assessed, feedback, multiple revisions, I'll put all of the files, the report, the presentation, the model, and any other supporting files. That'll be all in a cloud folder, and I'll provide the link to you to download that. Probably somewhere towards, well, it'll be in May. Say probably the end of the first week or into the second week of May. By the time we get everything together, I tend to do it for all of our companies, all of our partners at the same time. And it just takes a little time to finish up the assessment and get everything wrapped up. So that's the time frame.
Okay, thank you very much, David. Okay, and I'll call this meeting to an end. And again, sincere thanks to everybody who's attended. I look forward to seeing this entire presentation on the Bowman Center website at bowmancenter.com. Thank you very much, everybody.